Greetings and welcome back. This is Dr. Gross. In our last video, we explored the two-way ANOVA, and that analyzed how multiple independent variables, or at least an independent variable with multiple levels, can interact to influence a dependent variable. We reviewed some assumptions like normality, homogeneity of variance, and the independence of observations. And before that, we covered the simple linear regression using height as the IV and weight as the DV. And this helped us to understand how a predictor variable, the independent variable, can explain variability in an outcome variable or the dependent variable. And so today we'll perform a multiple regression analysis. And this builds on a simple regression by including multiple predictors. And they can be continuous or categorical. Multiple regression, as kind of the name implies, evaluates how multiple predictors can affect an outcome variable or a dependent variable. We'll look at some assumptions again. Some will remain the same, like normality and linearity. However, the multiple regression model introduces some new checks, some different assumptions. So we'll take a look at multicollinearity, and that tests whether predictors are overly correlated. They're too alike. Independence of residuals. And we'll look at a Durbin-Watson statistic to assess that. And homoscedasticity is how you pronounce that. And that shows that residuals should be evenly distributed. And those checks will validate the results and confirm that they are reliable results. So before we jump into the multiple regression, let's go ahead and launch your SPSS. And when you open it on your desktop, this splash screen will appear. I generally close that. And now I have my SPSS open. And so a quick refresher. You have two views that you're working in, data and variable view. So this is data view, and this is where you input the data. The rows are your participants, and the columns are your variables. And this is where later we'll input new variable data. And we'll do some dummy coding of the previous variables, diet type and exercise level that we've input. And I'll explain why we're doing that as well. And then you have variable view. And I can switch to that right down here. Variable view is where you define the attributes of your variables, like the name, the type. It's generally numeric. String would be words. It's a simple way to say that. And labels help us kind of give context to the variables, describe them a little bit more. Values is where we code them. And lastly, our measures. And that's where we're setting them as nominal, ordinal, or scale variables. And that lets SPSS know how to handle the variables during analysis. And this becomes important today when we dummy code, and I will explain why. Some particularly useful features that I don't know if I've mentioned necessarily before. The label column I did describe lets you add some descriptions, and the values column, again, we use that to code diet type and exercise level with the following codes and descriptions. I suppose I could go ahead and open our expanded data set that we saved last time in our last video. And this might give some context to what I'm describing. All right, so again, our values column, we use this to code our variables. And if I click on that ellipses, you can see the value labels that we described, 1, 2, and 3 for low balanced and high calorie, and did that by adding. We can also take away. And over here is where we set our measures. If they are categorical, we're nominal scaling them. And if they are continuous, we are scale measuring them or setting them as a scale measure. So now that we've looked at, and there's data view again for you. And here are my value labels button, and I can click that and switch from code to description, which is useful. I like to keep it on descriptions. And now that we've reviewed the basics, let's talk about dummy coding and why we need to do it for this analysis. And I will lead you through it step by step. So it's a method, and we're going to convert this categorical variable into binary variables, zeros and ones. And that's really important because regression models require numeric input, and categorical variables like diet type with multiple levels, SPSS can't directly analyze that. Dummy coding allows for comparison of each category to a reference group, which we define. For instance, for diet type, we're going to set the low calorie as the reference group. And the dummy variables we'll set up will compare the balanced and the high calorie groups against the low calorie group. So why was it not necessary before? You know, we did an ANOVA, we did a linear regression. This is a multiple regression. Why didn't we have to dummy code then? Good question. In the ANOVA, SPSS can handle categorical variables directly without dummy coding because ANOVA tests group differences based on the levels of the categorical variables. So for instance, diet type, we had levels 1, 2, and 3 without requiring any kind of numeric transformation. In the regression, the linear regression, the simple linear regression that we did, it wasn't necessary because we used a continuous variable, height, and not a categorical variable. We tried to predict weight based on height. And so linear regression naturally handles continuous variables. It actually assumes everything you're using is a continuous variable. And that's where we might run into problems with these categorical variables. So in contrast, the multiple regression that we're doing today, it requires the dummy coding because it includes continuous predictors like height. And if that's all we were using, we wouldn't have to dummy code. But we're using categorical predictors too, diet type and exercise level. And without dummy coding, SPSS would just treat the categorical variable as a continuous variable. It would assume an ordinal relationship that 3 is greater than 2 and 2 is greater than 1, which would lead to incorrect interpretations of the output because these are categories, right? 1 is not necessarily less than 2. It's just different. It's a different category. And so in this multiple regression, we have 2 categorical variables that I want to use, diet type and exercise. And so to include them, we need to dummy code them. So SPSS treats them as a category without assuming an ordinal relationship. All right. So by dummy coding, then, we can see how each diet and exercise level affects weight compared to the reference group, which we will set. Low calorie diet and low exercise will be our reference groups. So let's get into it. Step by step, here's how we're going to do it, setting up these dummy variables. The reference group we have identified. So we'll say diet type, low calorie, 1 is the reference group. And for exercise level, low exercise, 1 is also our reference category. So to create these dummy variables for diet type, we're first going to go to variable view. I like this side-by-side setup. I feel like it's easier. I hope it's easier for you. I'll go to variable view, and in my first available row, number 8, I'm going to add a new variable. We're actually going to add 2 new variables, but in row 8, let me scroll over to the beginning. In row 8, I'm going to add a new variable, and we're going to call it diet underscore balanced. And the type will be numeric. The width is fine. Decimals, let's say 0 in this case. For the label, 1 we can say is equal to a balanced diet, and 0 is any kind of other diet other than balanced. No need to mess with the values. The only other thing we'll do is we will set the measure to nominal, as these are categories. All right, so and then we're going to set up another dummy coded variable, and this is going to be called diet underscore high calorie. In this case, I have used my name with the underscoring and the camel case. So there's a good example of two different ways in one to do it. So we have the name. We'll set the type to numeric, which is default anyway. Again, for this one, I'm going to set the decimals to 0, and I'll explain why when we get there. Let's add a label. In this case, 1 will represent the high calorie diet. I don't want to do high calorie diet, and a 0 will represent any other kind. Again, the measure will be nominal as these are categories. And so let's create our dummy variables now for exercise level, since we're already in variable view. So now we're going to add 2 more variables. We will name in row 10 this exercise underscore moderate. The type is numeric. That is default. Again, I want to set this to 0. I'll show you why in a little bit. Our label for this one, 1 will equal moderate exercise, and 0 will equal any other form of exercise, so high or low. Lastly, the last thing we'll do is set this to nominal as its category. All of these will be. And lastly, exercise underscore high is our last dummy variable, numeric. Again, 0 for the decimals for our label. 1 is going to equal a high level of exercise. High exercise, let's say, and 0 then will equal any other level of exercise. Set this to nominal. And we have our 4 new dummy variables, or dummy coded variables they will be. Just trying to make this look a little bit better. That looks okay. Sure. And okay. And I can see the 4 new variables that I have. And now we can switch to data view, which we're already in. And I went from variable to data view. And for each participant now, 1 through 32, I'm going to assign values to the dummy variables based on their original categories. And I'm going to do this with you. So I apologize for the length of this video, but I'll try to do this fairly quickly. And so for the diet balanced variable right here, for any diet type that is balanced for any participant, I'm going to enter a 1 on this new variable. So all I'm looking for is I'm going down diet type, and anytime I see balanced, which is a diet type of 2, or coded as 2, then I'm just going to enter a 1. And there's not very many of them, so that's good. So here's diet type, and I can see the ones that are balanced. So for these that are balanced over here, I'm going to indicate that as a 1. And so then I'll just go down the list. And again, I'm looking at diet type and I'm going down and I see this high calorie. Here's a balanced. So I'm going to enter 1. Low. Here's another balanced. Here's a balanced. And no other one is balanced. So for all of those, I can enter 0. 0 for all others. So let's do that pretty quick. All right. And moving on. I told you I was going to try to do this quick for you. High calorie diet. So we're going to enter 1 for participants with a diet type of 3. Remember, we're not messing around with low calorie. Low calorie is our reference, right? So we're only counting for the balanced and the high calorie diet types for our dummy coded variables. So for, again, diet types of 3 or high calorie, we're going to enter a 1. So I'm going to go over here for my dummy coded variable. High calorie diets is what I'm looking for. And that helps me to name it that way too, balanced and high calorie. So again, I'm referencing the diet type. And for any high calorie diet, I'm going to enter a 1. So I see low, balanced, high, balanced, low, balanced, high. Right. And so I've identified all the high calorie diets. So for all the other ones, I can enter zeros. All right, and I've got 2 more to go, and so we'll move on to exercise. So we just did our dummy coded variables for diet, both balanced and high, with low calorie being our reference. And now we're moving on to the exercise. So again, for moderate, anytime I see moderate exercise, I'm going to enter a 1. And those are the only moderates. So I'm going to go back up, and for all others, I'm entering a 0. And lastly, high exercise. So again, for any case that I see a level of high exercise right here, or maybe you're in variable view, anytime you see a 3, you're going to enter a 1. So I like to keep it this way. So anytime I see high exercise, I'm going to enter a 1. And right here. Right. And then for all others, a 0. All right. And so that takes care of our new variables with our dummy coding so that SPSS recognizes this as a category and not as an ordinal variable. And so this is what it would look like. And, I have that example for you here. So again, by dummy coding, why are we doing it? These categorical variables, we're preparing them for analysis. This allows SPSS to compare group effects accurately. And we'll definitely want to save our data set now. So I'm going to go to File and Save As, because I'd like to be able to differentiate. And this is my expanded data set, but it is expanded with dummy codes. So I'll kind of save that as a new set, different from our other set. So now that we've created and entered the dummy coded variables, we're ready to run the analysis. So step, we'll go to analyze regression linear. And we'll see the linear regression dialog box open. I'm going to move that over. And step 2, let's define the variables. So we're going to move dependent variable, or we'll move weight to the dependent variable box. So here's weight. And I can drag and drop, or I can select and click. So my independent variables will have a few. We're going to add the following. Our continuous predictors are going to be height, point and click, and age. Again, I'll point and click. And then our dummy coded categorical predictor variables, all 4 of them, balanced and high diet, and then moderate and high exercise. So let's add all 4 of those. Let's write below exercise amount. Balanced and high calorie diet, and then moderate exercise. And just for fun, high exercise, I'm going to select and just move that over. Step 3, let's configure our statistics for our assumptions so we can meet and talk about those. And then we'll configure the model for testing. So the first thing we're going to do is click stats, and right here, I'll see that dialog box open. I'm going to move it over so we can see. And I'm going to select estimates, which is already selected. That provides the coefficients for each predictor and their significance. So we'll talk about those in the output. The model fit, which is already selected for you as well. This generates R squared and the adjusted R squared values. And this is an explanation of how much variance can be accounted for by the model. And we'll talk about that. And we want to click on collinearity diagnostics. This is going to check for the multi-collinearity assumption and whether these predictors are too highly correlated with each other, which could end up distorting the results. And so we'll click. I don't want to click continue yet. I know it says that, but I don't want to click that yet. I'd actually like to click this Durbin-Watson statistic too to check another assumption. So I'm going to click that, and now I'll click continue. And now we want to go to plots to test some assumptions. So I'm going to click on plots, and let me move this dialog box over so we can see. I'm going to add Z predicted, our predicted values, to the x-axis. So here's Z pred, or Z predicted, and I'm going to move that to the x-axis. So I'm going to select it, click it over here to the x-axis, and then Z residuals, standardized residuals, over to the y-axis. So here's Z resid, or Z residuals, and I'm going to move that over to the y-axis. And this is just going to generate a plot for us, residuals versus predicted. And this is going to check for a couple of things, both linearity and homoscedasticity. What should you be looking for? You should be looking for linearity, the residuals should kind of scatter. So no pattern. However, for homoscedasticity, you should have a kind of a consistent spread across the predicted values. The final plot we'll check will be the normal PP plot, and that checks normality. So the residual should kind of follow a diagonal line or straight line. So I'm going to click histogram and the normal probability plot, or the normal PP plot, and click continue. And so now I am set up to run the analysis, so I'm going to click OK. So several key outputs here. You can see the model summary right here. And this is going to include your R and your R squared and your adjusted R squared. And we'll talk about all of those. And technically, this is just, it's showing you how much variance in weight is explained by these predictor variables that we used. You'll see the ANOVA table, which tests the overall model significance. In this case, our overall model, our regression model, was significant. And then you'll see the coefficients table. And this is going to provide the unstandardized coefficients, your B values, your significance values, or your P values, and your collinearity diagnostics, which are going to be over here. And that includes tolerance and your variance inflation factor for each predictor. And I'll talk about that output and what it means. You're then going to have a residuals plot. Here's your residuals plot. And you'll have your collinearity diagnostics table, which is right here. So, what are we looking for when we assess these tables? And we'll look at them all individually in just a second. For the model fit, you're looking at R squared and the adjusted R squared. So these two right here in the model summary table. And that tells you again how much of the outcome variable, the dependent variable, how much of the variance in that is explained by these predictor variables, these independent variables that we used. In the ANOVA table, you're looking for model significance. So was this statistical model significant or able to detect significant differences? For our assumptions, here's what we're looking for. In the plots, we're looking for a random scatter in the residuals versus predicted plot. For homoscedasticity, the residual should have kind of a consistent spread across predicted values in the same plot. That would look like a funnel shape. And so we'll look at that. Normality, we'll look at the PP plot. Should kind of follow a straight diagonal line. And then multicollinearity, we'll check the collinearity diagnostics table. And in this case, we're looking for tolerance values below 0.1 or VIF values above 10. Those would indicate a problem. So we'll look at that. Finally, or maybe not finally, but the individual predictors would be in the coefficients table. So we'll look at the B values, and those indicate the effect size really for each predictor. So how much did each predictor weigh in? How much variance did it actually account for individually? Is a good way to kind of look at that. The significance of the p-values, that shows whether those predictors meaningfully contributed to the model, made a significant contribution or significant predictors. And so hopefully you've already run the analysis. And if you have, then we'll go ahead and interpret each of those that we just looked at. So let's take a look at the model summary, and we got an R of 0.965 and an R squared of 0.931 and an adjusted R square of 0.912. And let's focus in on these. R squared is telling us that 93.1 of the variance in weight is explained by these predictors that we used in the model. That's a very high percentage. That suggests that the model fits very, very well. Adjusted R squared is still very high. 91.2% of the variance in weight can be accounted for by the predictor variables that we used. And the adjusted R square accounts for the number of predictors that we used. So did we use 2 predictors, 3 predictors, 100? Now, we clicked the Durbin-Watson box when we were setting up the model. So here's that Durbin-Watson statistic in the model summary box. Right, we're still in model summary. And that Durbin-Watson statistic is 1.873. And how do you interpret that? A value near 2 indicates no autocorrelation, which is a good thing. So 1.873, how would we interpret that? Our model explains over 93% of the variability in weight, which is very, very good. The Durbin-Watson stat of 1.873 confirms that the residuals are in fact independent, and that meets one of our assumptions for the model. Let's look at the ANOVA table next. F value is right here of 51.33, and a p-value less than 0.001, which is significant. And again, we would interpret that by saying this tells us that at least one of the predictors significantly contributes to explaining the variance or the differences in weight. The overall model is effective and meaningful for predictive purposes. We then move on to the coefficients table, and let's look at what these are. So the unstandardized coefficients right here, and these B values, these show the change in the dependent variable, weight, for a 1 unit change in the predictor variable. This is assuming that all the other predictors are held constant. So next, the standard error, that indicates the precision of each coefficient's estimate. The t-value and the p-value. P-value would indicate significance, whether each predictor contributes significantly to the model. And again, we're looking at less than 0.05. And so we can look at, is height a significant predictor of weight? And in this case, it's not less than 0.05. So height in inches is not a significant predictor, although it's close. Age, it seems to be a very significant predictor, less than 0.001. Exercise, moderate exercise is not. High calorie is not. Balanced diet is not. But this one is high exercise, less than 0.05. So a significant indicator by itself if these are held constant, right? Lastly, you'd have these standardized coefficients, and this would indicate the relative importance of each predictor. So again, unstandardized importance by themselves, and then the standardized importance relative to one another. So let's take a look at each of these values, right? So for height, a B value of 1.707, a P value of 0.70. So I'm sorry that repeated. For every 1 inch increase in height, weight increases by 1.707 is how we would interpret that statistic. However, it's not significant. Age, was age significant? Yes, very significant. So I age right here, and I'm going over to the significance value, less than 0.001. And how you interpret this is for every additional year of age, weight increases by 2.231 pounds. And that is statistically significant, indicating that age is a meaningful predictor of weight. And we can look at the balanced diet, and negative 4.773, but again, not significant. And what this would indicate is that the balanced diet group weighs 4.773 pounds less than the low-calorie group, which was our reference group. But again, it's not significant. Lastly, the high-calorie diet was significant, 0.015, less than 0.05, so that's significant. And in this case, a B value of negative 26.666, and I'm not sure why this is as incorrect as it is. Now let's erase this. This is not right. So let's look at the high-calorie diet, which is significant, 0.015. And so what this is saying is that for those who engaged in, well, that's why I'm looking at something different. Let's look at the high calorie and not the high exercise. So for high calorie diet, yes, 12.573 with a p-value of 0.211. That is correct. I don't know why I repeated it, but I must have hit control paste too many times. So how you interpret this then is the high calorie diet group weighs on average 12.573 pounds more than the low calorie group, which was our reference. But again, not statistically significant, 0.211. There's what I was looking for or looking at initially. Moderate exercise group. Here's the moderate exercise group. It's not significant. So we won't really look at it, though they weigh 12 pounds less than the low exercise group. The high exercise group, though, that was a statistically significant predictor. So the high exercise group weighs 26 pounds, 26.6 pounds, repeating, less than the low exercise group, which was a significant difference, 0.015. So let's look at the multicollinarity diagnostics. That's over here. So tolerance and VIF, the variance inflation factor. Tolerance values, should be less, or should be greater than 0.1. Anything that's very close to zero would be an issue. And for a variance inflation factor, anything above 10 could be problematic. So for us, we're really not approaching zero in any case. Really not above 10 in any case. We're close, in a couple of instances. So for the high calorie diet and the high exercise, tolerance is it's getting closer to zero. It's closer than the other ones. And the variance inflation factor is 8, so it's high. It's elevated cholinarity, but not above or below those critical thresholds. So we're safe. So how would we interpret that? Well, there are some signs, particularly for those two variables. They're within the acceptable limits, so good to go. Let's take a look at the normal PP plot. So here's the normal PP plot of regression standardized residuals. And so the residuals, do they follow a roughly a diagonal line? Yes, they do. Here's that line of best fit. It's close. Pretty good. So yeah, they closely follow that diagonal line. So the normality is met. Residuals versus predicted. So here's our residual versus our predicted scatter plot. And do they scatter randomly, without a clear pattern? If so, which I believe they do, this suggests linearity and homoscedasticity have been satisfied. So the residual plot confirms that the model meets the assumption of linearity and homoscedasticity and normality. So that ensures the validity of the results, gives us more confidence. So how would we interpret this altogether? we would say that our multiple regression model is statistically significant. Right, here's that regression model significance, and it is. And we would look at the R squared value, and we would say that our model accounts for 93.1% of the variance in weight. Among the predictors, age and high exercise were significant. Other predictors did not show statistical significance in this sample. And how would you write that up? A short example right here. And this differs, I suppose, by professor, by institution, by publication. So kind of just an easy example of how you might write up the results section for this and how you might discuss it. Again, these are very, very short kind of examples, but just as an example. So today talked about multiple regression in SPSS, and we looked at dummy coding, why it was important for today because of our use of categorical variables in the regression model. And we walked through those dummy codings, setting up the regression model and making sure that the assumptions were all met, including the linearity, normality, homoscedasticity, and a newer one, multicollinearity today. With the results in this model for this sample demonstrated a significant model explaining 93.1% of the variance in weight. I think some key takeaways that we should mention here at the end, understanding how to interpret those coefficients, R squared values and significant values, understanding the unique contributions of different predictors and if they are significant, and then understanding the different assumptions today for the multiple regression model. And hopefully this highlighted the usefulness of multiple regression for making predictions based off of multiple variables. So next time we will look at another statistical model in SPSS, and I hope that you have found these videos useful. It's Dr. Gross signing off, and we'll see you next time.